Hi, welcome to the webinar. My name is Thomas and this is Miguel, and we are applications engineers at the MPS office in Barcelona. Today we come to you, as Enrique told you, from the MPS Now Lab, which we've created to help solve any problems that you may have with our technology. So now let's move on to the presentation about flyback converters. With us today are also Gary Church and Ilkay Sala, who are field applications engineers for the UK, West Europe and Northeastern Europe. And they'll be helping us answer any questions that you may have at the end of this presentation. This webinar is going to start with an introduction into the flyback topology, talking about the power range, applications, and advantages and disadvantages of this type of converter. Then we're going to see what MPS offers regarding flyback converters. And after that, we're going to take a look at the fundamentals of the flyback converter, followed by a simple example using the MP6004, a flyback controller that can be used for a PoE application. Finally, we're going to perform a demonstration on how the flyback design works on an evaluation board, and then we're going to be answering your questions in the Q&A. So the flyback converter is a switch mode power supply that is widely used in low to mid power applications for AC-DC or DC-to-DC conversion. This converter could also be described as a buck boost, but with a coupled inductor. Because the flyback is an isolated converter, it can have multiple outputs and guarantees isolation between the input and the output, which is useful in a wide variety of applications. Regarding power, it is mainly used from 2 watts to 100 watts, where it has a good size, cost, and efficiency ratio. As power increases, however, the transformer starts to get too big, and then the LLC converter is preferred. Considering its ideal power range and its galvanic isolation, the flyback converter has a lot of applications, such as low to mid power multi-purpose power supplies, multi-output power supplies, high output voltage generators for lasers and displays, isolated AC-DC converters for wall adapters, phone and laptop chargers, etc., as well as DC to DC power conversion. And it's also useful for telecommunications equipment and, as we are going to see today, power over Ethernet applications. It also has multiple advantages over other topologies, such as the low component number, which leads to low cost, galvanic isolation between the primary and secondary, which are separated by the flyback coupled inductor, the possibility of having multiple outputs, a wide input voltage range and load conditions, and the possibility of generating high output voltages. It also has the capacity to step voltages both up or down. But it also has disadvantages, like a relatively low efficiency of around 75 to 90%. This depends on a great variety of things, such as the input voltage, the number of outputs, the output power, the component parasitics, etc. It also requires input filters and a transformer, which take up a lot of space, and voltage and current spikes may occur on the switches and can be very high depending on the application or design. So among all the applications of the flyback, a very important and interesting one is the power over Ethernet. This technique is used in applications that cover a wide range of powers and voltages, which overlaps the power range that the flyback excels at. So from supplying an IP camera to smart lighting, flybacks can be key for your power over Ethernet applications. Now let's take a look at MPS's flyback controllers. At Monolithic's power systems, there's a great variety of flyback controllers from DC to DC to AC to DC, and covering a multitude of power ranges, input voltages, and different operation modes. And we also have the possibility of primary or secondary regulation, which we'll go into more into further. They also provide many features with minimal external components. And if you're interested, we suggest that you find more information on our website, monolithicpower.com. In addition to typical flyback controllers, we also offer a variety of IC for PoE applications, PD controllers, PD plus DC to DC controllers, like the MP8009 or the MP8007H, which are highly integrated power over Ethernet solutions. So now let's go into understanding how the flyback converter works. This is the main simplified schematic of a basic one-output flyback converter. Its main components are as follows: the MOSFET, which is used to control the converter's operation; the input capacitance, which filters out any high-frequency noise in the input voltage; a transformer, which provides the isolation and the multiple output capacity. But this is actually a coupled inductor, which stores the energy from the input and transfers it to the output. And finally, we have the output rectifier and the output capacitor, which deliver the DC voltage to the output. We will begin with a short explanation of the topology of the DC-DC flyback converter. We are going to analyze its operation and extract the transfer function. So we will operate in continuous conduction mode, but we will also see DCM operation later in the presentation. When a flyback converter operates in transition mode, or CCM, it has two different phases, which we will call T-on and T-off in reference to the MOSFET state. During T-on, the input voltage across the primary side of the transformer creates a current across the coupled inductor, which will linearly increase and charge it. In the secondary half of the converter, the secondary rectifier is reversed biased, disconnecting the transformer from the output. This means that only the output capacitance is delivering power to the output load. During T-off, the MOSFET is open and the coupled inductor begins to demagnetize through the diode, which is now directly polarized. The current from the inductor then charges the output capacitor and powers the load. This is called continuous conduction because the inductor is never demagnetized completely. When working in DCM, the converter enters a third state in which the inductor is demagnetized and that both the MOSFET and the diode remain in an off state. We will now extract the transfer function of the flyback converter, and we will do so by applying the state space averaging technique, which we'll talk more about shortly. First, we will use the voltage at the primary inductance to extract the needed equations. If we analyze the converter in transition mode, during T-on, we know that the voltage at the primary inductance is more or less equal to the input voltage. Also, the T-on is the time equal to the duty cycle times the switching frequency. The instantaneous inductor current can be calculated as the slope of the triangular waveform of the input voltage over the inductance at that particular time. And therefore the peak will be at the end of the on time. During the second stage, in which the MOSFET is off, the voltage at the primary inductance is the output voltage reflected through the coupled inductor. So where N is the transformer turns ratio, the primary turns divided by the secondary turns. The current in the primary inductor for this stage is 0, and T-off is the remaining switching period time. We can now rewrite the voltage at the primary inductance equations using the value for the on and off times we've defined before. And finally, we can apply the volt-second rule, which states that the average voltage across an inductor or capacitor at steady state is 0. This means that we can equate both expressions and finally obtain the simplified transfer function. As you can see, it clearly relates the gain of the converter to the duty cycle and the transformer turn ratio. So now that we've found the transfer function, let's focus on the current in the flyback converter. First equation has been extracted from the past slide in transition mode by substituting T-on over D over the switching frequency, where the switching frequency is the inverse of the switching period. This would be the primary current ripple. Now, because we're analyzing the circuit in transition mode, which is the point between continuous and discontinuous current mode, this ripple would also be the primary current peak. However, if we are working in continuous current mode, as the waveforms on the right, we would have to do a quick analysis to get the DC component of the magnetizing current and add it to the positive half of the ripple. Then, using the transfer function, we can express this as an equation, this equation as a function of the power requirements. We can also find the RMS current values for the primary and secondary using the general equation for a pulsating waveform with a linear ripple. And then we input our current related to the output, and we can establish the primary and the secondary RMS currents. Now let's look more closely at the voltage. The voltage values that we're most interested in right now are the maximum voltages across the MOSFET and the diode. This is because we need to know exactly how much electrical stress we're applying to these components. So the first equation is for the maximum drain voltage of the MOSFET. This peak will take place while the converter is in the off state, where the voltage difference between the drain and the source will be the addition of the input voltage and the voltage reflected from the output. Using the transfer function, we can rewrite this equation to be defined only by the input voltage and the duty cycle. Now is a good moment to remind you that these equations are simplified and do not consider factors such as the auxiliary windings or parasitic components. The real maximum voltage that the MOSFET will have to withstand is the peak voltage provoked by the leakage inductance and the drain capacitance of the MOSFET, which will create an even higher voltage peak. Therefore, safety margins will have to be added to the component calculations in order to make sure that the MOSFET and the diode don't break down because of these non-ideal characteristics of the components in the converter. Finally, regarding the diode's maximum voltage, the worst case is during T on, where the diode is inversely polarized and the voltage across it is the output voltage plus the input voltage reflected through the transformer. Aside from the main voltages and currents, there's a large variety of other parameters that we have to take into account. We're going to go into a few of the most important ones, which include the differences between CCM and DCM, how to choose the ripple factor, choosing the right switching frequency, what side will perform the regulation on, and how to determine the maximum stress applied to the MOSFET and diode through setting the maximum duty cycle. First of all, what's the difference between CCM and DCM? Well, basically, the main difference is that in CCM, the coupled inductor is demagnetized in every cycle. So in other words, there's a moment where the current flowing through the MOSFET and the diode is zero. In the top current graph for CCM, you can see how the current for both the inductor and the MOSFET never reach zero, whereas in the bottom DCM waveform, there is a space between the complete demagnetization of the secondary inductor and the recharging of the primary in the next cycle. We often get questions about the differences between the CCM and the DCM. So let's compare both conduction modes. And to do so, we're going to fix the same input voltage, the same duty cycle, and the same switching frequency. One main difference is that CCM offers less efficiency than DCM because there are losses in the secondary diode because of the reverse recovery, whereas DCM offers a softer turn-on in the MOSFET. However, if the duty cycle is too small, then the current that charges the primary will have to be really high. So we'll end up losing efficiency there also. And this indicates that we have to choose a reasonable duty cycle for DCM. Regarding the transformer size, at DCM we need a smaller inductance, which would mean a smaller transformer. But due to the incremented spikes of the primary and the secondary current, the transformer wire gauges would also have to increase, which will mean that both transformers will be more or less the same size. However, during DCM, there is more efficiency than in CCM, so we may increase the switching frequency and thus accomplish a smaller transformer. Sorry, before we move on, another important factor to take into consideration is that the flyback in DCM operation is easier to compensate than in a CCM flyback. So this has to be taken into account when designing a system. Next, we're going to discuss the KFR, the ripple factor, which is going to help us calculate the minimum value for our inductance. This parameter basically allows us to decide in which operation mode the flyback will be working, either in DCM or CCM. We will define the ripple factor parameter as half the current ripple over the current's DC component. We'll start with the peak primary current that we found in the previous slides. We can write the ripple factor with the following equation, where half of the current ripple is divided over the DC current in the primary. If we rewrite this equation, we can finally extract primary inductance that will satisfy our working mode conditions and ensure that the converter works in either DCM or CCM for all conditions. So If we want to work in DCM, we would have to set the ripple factor to approximately 1. Whereas if we want to operate in CCM, we're going to have to establish a KFR of between 0.3 and 0.4. Another important aspect of the converters to design is the control loop. Our converter can be split in 2 parts. We have a power path and a control path. Today, we're not going to go into the design and the operation of the control path. We're simply going to go over it briefly. But there are many different control techniques. We're not going to enter into many details about this, but for example, the voltage control mode, which is the most basic control method, uses only an output voltage feedback loop. We will use the peak control current mode, which is the most common method and has a set of advantages. Current mode is a modification of the voltage mode control, where aside of the output voltage, there is an inductor current in the primary winding, which is also sensed. Let's start with primary regulation. This is a simplified schematic of an AC DC flyback with an MP020A5, which uses primary regulation. In a real application, a controller's IC needs an auxiliary output from the transformer to supply the IC circuitry. This auxiliary output is directly related to the voltage at the output. And because we know the transformer turn ratio, this output can be used to regulate the system. This method allows us to roughly regulate the output with very few components. So on the other hand, it makes output voltage more susceptible to load changes. Furthermore, if there's more than one output winding, this susceptibility can be even greater. If we decide to use secondary side regulation, we'll find that the regulation is more accurate, even when there is more than one output in the secondary, because we can use different techniques to optimize this regulation, such as escalating the windings of the transformer or using a weighted feedback technique. We don't have time to go deeper into this, but we're going to look at how different control loop techniques improve converter regulation in future webinars. But now we're going to move on to the switching frequency selection. The general rule states that if switching frequency goes up, the transformer size and filter sizes are reduced. But switching losses due to non-idealities, such as the drain capacitance of the MOSFET, go up. Therefore, we're going to have to find a compromise between size and losses. Another parameter that we need to take a look at is the duty cycle, which, remember, is the ratio between the primary side switch on time and the total switching period time. In the flyback, duty cycle is important because apart from determining the output voltage with a given load, it also determines the MOSFET and rectifier diode stress. For example, if we work at low duty cycles, the stress of the MOSFET will rise. But if we work at high duty cycles, then we will have a greater stress of the diode. We must therefore set a maximum duty cycle so that when working in the worst conditions, that is at full output power and minimum input voltage, we achieve practically equal minimum stress and equal utilization of both the MOSFET and the diode. This must be done both when working in DCM and CCM. And if there are other constraints of design, then we can favor the MOSFET stress or the diode stress by changing the duty cycle. So after seeing the flyback's fundamentals, we're going to see a simple design example of the flyback converter. This is the simplified design flow that we're going to follow. First, we have the user inputs, which are all either known or decided by us. Then we're going to calculate the maximum inductance not to surpass the KFR ripple factor we will fix. And then we're going to calculate the turns ratio and finally determine the remaining parameters in order to select the components for our design. So we're going to start with the design inputs. We have our input voltage range. In this case, we've selected an input voltage of 36 to 72 volts and an output voltage of 12 volts and a 1 amp at the output. We will also decide to operate in DCM due to the increased stability and the higher efficiency it can achieve. And we're going to fix the maximum duty cycle at 0.5 and a switching frequency of 160 kilohertz. Finally, in order to make our calculations more realistic, we're going to define an estimated value for the efficiency of the converter. We will estimate this efficiency to be relatively low, as this is a low power flyback converter, which are notorious for having low efficiencies. We're going to select for our application an MP604, which is a flyback controller that only works in DCM. It also has a primary side regulation, reducing the part number count drastically, and a maximum voltage of 80 volts at the input, an integrated 180 volt switching power MOSFET, and an internal 80 volt startup circuit, which can stand up to 3 amps and has a wide range of protections. Our first design calculations will be to find the maximum primary inductor value. There are many different design methods to find this value, but we will try to find the maximum the maximum value for this inductor to keep the converter working in DCM for all operation modes. In this case, our worst case comes from the converter working at full power, but with minimum input voltage and maximum duty cycle. We've set KFR to 1 for these conditions, and therefore we've got to limit our inductance to 53 microhenry. If we implement this inductance, we would be working at boundary mode, so just at the limit between CCM and DCM. Next, we calculate the required turn ratio. To do so, we apply a worst case scenario with a minimum input voltage and a maximum duty cycle, and we add the diode's forward voltage drop to make our calculation more precise. So we're going to design a transformer with 2.5 times more turns in the primary than in the secondary. Next, we have to make sure our MOSFET is right for the application. To do so, we have to calculate the maximum current and voltage it will have to withstand. We will use the equations we found in the first part of the presentation to do so, and we're going to add a 20% safety margin to account for the peak. Remember that the MP6004 has a 180 volt power MOSFET and can take up to 3 amps. So with these calculations, we can see that we can use this controller IC without any worries. There are other important parameters of the MOSFET to take into account which can affect our converter, such as the equivalent resistance, the parasitic capacitance, the power dissipation, and the rise and fall times. But we are not going to study them in this webinar. So next, let's select our rectifier diodes. In the MOSFET, we have to make sure it can handle the maximum voltage and current it may find in the circuit. Using the equations we defined previously, we have to calculate the maximum reverse voltage to be 57.1 volts, and therefore we set the forward current to 2 amps, twice as much as the output current. As in the MOSFET, other important parameters are forward surge current or reverse recovery time, but it's important to consider for more accurate component selection, but in this case, it isn't necessary. To calculate the value of the output capacitance, we can make an approximation where we ignore the parasitic elements of the capacitor, as well as the effect of having multiple outputs. The capacitor can be set knowing the voltage ripple that is applied through it is equal to the equation shown here. We will analyze it at T-on, where the current in the load is the same as the one exiting the capacitor. If we perform the calculations, then we're going to come up with the following equation that will relate the value of the capacitance and the output voltage ripple. We then have to select a capacitor value, which gives us a desirable ripple voltage, such as the 250 microfarad capacitor used in this example, which means that the voltage ripple at the output will be 12.5 millivolts. The next design step involves the transformer. There are many design decisions to be involved in choosing the transformer. We have to choose the core material and the core shape, both of which have multiple options available, each with its own specific advantages. In our case, we're going to choose a common ferrite core in a double E shape. If we were working in CCM, we'd have to do a deeper analysis of the magnetic core losses because the average flux in the transformer would be higher. Next is the bobbin. This component gives us both the structure to support the core, the safety creepage distance, and the number of pins in our transformer. Then we have the wire gauges, which have to be set depending on the currents that flow between the primary and the secondary. And the final parameter we have to define is the maximum voltage we can apply while maintaining isolation. If we apply a voltage above the limit, there may be current leakage and the secondary will no longer be isolated from the primary, resulting in potential damage to the devices connected to the secondary and even danger of electrical discharges on the user. So this is a very important parameter. The method we're going to use to calculate the area of the transformer is called the AP method. It defines the total area of the transformer as the product of the winding window area and the area of the core cross-section, where all the transformer's magnetic flux is concentrated. Now we've defined the method and the design parameters, let's do a quick set of calculations to design our transformer. First, we calculate the minimum area for our transformer, so we select a core that is larger than this minimum value. In our case, we've chosen an EE13 core and a bobbin with a minimum wire gauge of 0.28 millimeters, sorry, 29 millimeters. Then we calculate the primary and secondary turns we can fit in the transformer, maintaining the turn ratio we calculated before. The last step is then to choose the wire gauges according to the currents and the switching frequency. The last step of the design process would be to find the values for the snubber. This circuit aims to dissipate the remaining energy at the leakage inductance at the primary while the converter is switching from T on to T off. The snubber helps mitigate the voltage spikes that occur due to ringing between the leakage inductor of the transformer and stray capacitances in the circuit at the switching node. Without the snubber, the voltage spikes could be very large and even damage the MOSFET, or at the very least, this would add a lot of noise at the converter. So this element requires a deeper analysis than the one we have time for in this webinar. So we've just left you with the equations and our final results, and we'll address this topic further on in future webinars. So after this design process, we've found the best values for our design, which you see here on the slide. What we're going to do next is observe how the converter works with a live demonstration in our lab. So now I'm going to hand you over to Miguel, who will explain our lab setup.
Thanks, Thomas. Well, I'm going to explain the PCB. This is the design that we made at MPS. Right now it's working at the lowest input conditions while maintaining 12 volts at the output. The design is a very small, compact solution that uses the MP6004 controller. This is the solution. We can see that this is our MPS controller. Here we have the input capacitance. The IC controllers contains the MOSFET. Then under this probe we have the snubber. This is the transformer, the Flyback transformer, and the output rectifier and the output capacitance. We can see that at minimum weigh-in, the maximum duty cycle achieved is around 0.5. This is 0.447. At the MOSFET, we can see that at low input, we get a maximum MOSFET current at 1.44 amps and 3.3 amps at the output diode. If we increase the voltage to the maximum voltage, 72 volts, we can see that now our converter is working at deeper DCM. The maximum MOSFET current is 1.5 amps. The maximum voltage at the MOSFET without the peak is 100 volts, and with the peak it doesn't exceed 125 volts. And at the output we have 3.2 amps peak current at the rectifier diode, and the reverse voltage peak at the diode of 60 volts, around 60 volts, 62 volts. Okay, so that's it. Thank you for the demonstration, and let's proceed to the Q&A.
Thank you, Miguel and Tommy, for your presentation. There is two questions right now. One is if the webinar will be recording. Yes, all these webinars will be available next week to MPS webpage. So everything will be posted online. Thank you. Then there is another question that says, what about ripple current in the input and output capacitors? How we can right capacitors be chosen to not overstress it?
Well, this is a simplified flyback design. So we consider that we just pick a big enough capacitor that can support that currents. But if we in the future we could do a more in detail webinar.
Okay, thank you. There is another question regarding one person who like to design a multiple output power supply using MP 6004. With the loading of one winding, change the voltage in the other winding?
Well, we can, if one output is loaded and the other is not, there is problems at the regulation. So we could use some techniques like the weighted feedback techniques at the output. And you should also regulate at the secondary. But yeah, there is a lot of techniques you can use to improve that cross regulation.
So, any other question regarding?
Oh, Henrik, do you hear me?
Yes.
Okay, if I go back to this side comments here for the first question about the this input and output capacitors.
Yes.
We didn't put everything on this presentation, but if you look at our data sheet, we have there the big chapter describing the input capacitor selection. So there's all the formulas and all the explanations in there. So please have a look. And secondly, to this multiple output, the question. First question is, what is the regulation you need between those different outputs, and how dynamic the loads are? If there's a big changes in the load currents, maybe it's a better idea to use a secondary side feedback instead of this primary side, because there you can use this weighted the feedback or the stacked output windings. Also, it's a good idea when you use a weighted feedback is to use the most stable output as the primary feedback, the more weighted than the rest. So the rest will follow. So typically the highest power output is the primary feedback. But that's another topic, and we are more than happy to assist you when you have a project where you are designing such. Okay.
We also have evaluation boards. Sometimes for high volume projects, we can also support to do a customized solution. Okay. Regarding if there is samples available, I think this product it's released so through distributors or through our FAEs, it will be possible to get samples, and I think even it's available in some major distributors. I will check it.
Also, if I may comment that the samples are always available. I think you can request them through our website. but also contact the DISTI, our local teams. And also we have the evaluation boards, which we are selling through our website at a very modest fee. I think it's like $25 or something, very reasonable. And they are very, very good help in your design. So for the 6004, we also have the demo board.
Yeah, I saw, for example, right now in Moser, there is evaluation board for this IC for 22 euros. So even the one is using Miguel is not in stock. But it should be in the future. But if not, as Ilka says, it's also possible to check through our website. We have a e-commerce service in our website. Then there is another question. It's what happens when we have a high duty cycle operation. I'm not sure if it means in terms of regulation or control.
In terms of, we have explained that at the presentation that if we set the duty cycle, a very high duty cycle, we will have spikes at the switches. Yeah. And we also have, we could have problems when working at CCM due to the difficult control loop design.
Thank you, Miguel. The same person regarding the sample says it's contact to a distributor in India and they don't have it. But I think if you are able to order through the e-commerce website, we can ship it worldwide from our centers in China. So you may try to go through our online platform, maybe. And if not, we can try to help you. So, is there any other question? If not, thank you for coming. As I said before, we have this new digital platform to support you from MPS Now Lab, so we can show you any device. We can help you to debug any problem you have with SLCs. We have this MPS Now in Spain, but also in US. So we can cover all the time zones, China and Europe, and also US time. And just you need to request through the website, and we can able to first contact by mail, and later if we need to do some call from our lab, it will be possible. So also to remind you, we'll have new webinars coming today in 1 hour regarding motor control. And then after in the afternoon, we have automotive, how to design a two-layers PCB for automotive and have a good heat and EMCs. And finally, one about high precision sensor for magnetic sensors. So you are welcome to come, and thank you for attending to this webinar, and we hope you have enjoyed. Thank you very much.
Thanks a lot. Goodbye.
Bye.